Hello everyone, let's continue looking into the interiors of the tri-state buffer, but before that let us try to identify the different transitions that will happen while you perform the function of a tri-state buffer. So for example, when your enable equal to 0, your output goes into the high impedance state. So there is a transition that will happen to go into the high impedance state. Now the transition can happen from either from logic 0 or logic 1. I'll get back to that in a minute from now, but there will be a transition that will be happening at the output 4 to enter into the high impedance state. Again, whenever your enable is equal to 1, there will be the output has to follow the input, which means if the output was in a high impedance state, it has to come out of the high impedance state and follow the input pin. Okay, so that's what there is another transition to come out of the high impedance state. Again, the transition can happen from logic 0 or logic 1, we don't know, but it has to come out of the high impedance state and enter into a known state, which could be either logic 0 or logic 1, depending upon what is the value of the input. So that brings us to a very interesting point on what will be these transitions be. So when we say the transitions to go into the high impedance state, it actually means is that the output enters into the high impedance state either from logic 0 or from logic 1. So the output might be at the initial state of logic 0, it enters from the logic 0 to the high impedance state, or if the output was logic 1 initially, it enters from the logic 1 to the high impedance state. Similarly, whenever your enable is equal to 1, output has to follow the in, but it has to come out of the high impedance state. Now the input could be either logic 0 or logic 1, so it has to come out of the high impedance state and enter into logic 0 state, or come out of the high impedance state and enter into the logic 1 state. So that's what that now you find there are 4 different transitions happening over here. So it will be basically logic 0 to high impedance state, that's what we mentioned over here, and then there will be either logic 1 to high impedance state. This happens whenever your enable goes to 0. So there are 2 different slew values that will be getting computed over here, and these are the different slew values that needs to be characterized for, and I'll get back to that how do we do that in the Guna tool in the part 2 course. Let us try to understand what do we need to do with the tool. Okay, second, whenever your enable is equal to 1, your output has to follow the input, but it has to come out of the high impedance state. Okay, so that's what it means. It has to move from the high impedance state either to logic 0 or from the high impedance state to the logic 1. So there will be 2 more slew values over here, and these are the 4 different slew values that needs to be characterized for. Now let's see how do we do it, but before that let us try to enter into the interiors of the tri-state buffer. So this is the interiors of the tri-state buffer. This has an inverter and a bunch of NMOS and PMOS over here. This circuit looks a bit complex, so let me try to simplify this one for you. So if you look into the each and every devices over here, if you look into this particular section of the circuit, this is a PMOS, this is an NMOS. The gates of the PMOS and NMOS are connected, or same thing over here, the gates of the PMOS and NMOS are connected, and if you bar the PMOS and NMOS which is present over here, this is nothing but an inverter circuit whose output is connected to the inverter of the next one. Okay, so this forms a back-to-back inverter connection, and that's why it's a buffer. So it's a very simple connection if you bar the PMOS and NMOS present over here. I'll get back to the PMOS and the NMOS in a moment from now. Okay, next what you have is if you look into the PMOS and the NMOS which is present over here, there is certain connections that is happening. The gate, the input of the gate of the NMOS is connected to the enable port, and the gate of the PMOS is connected to the inverted version of the enable pin, which is called as enable bar. So whenever your enable is 1, your NMOS turns on, your PMOS turns off because it's enable bar, and this forms as a short circuit. So this complete thing behaves as a CMOS inverter. Okay, so that's how the circuit becomes more simplified. Similarly, the enable bar is extended to the PMOS which is connected over here, and the enable pin is also extended to the NMOS which is present over here. So this is the enable pin goes to both the PMOS and the NMOSs. So this exactly forms as a back-to-back buffer connection, and this will behave as a buffer, or your output will follow your input only whenever your enable is 1, because whenever your enable is 1, your NMOS turns on, this forms a short circuit. Enable bar will be equal to 0, your PMOS turns on, these two will be a short circuit, and this behaves as an inverter, this behaves as an inverter. Your output will follow the input. Sorry, this is the input. Your output will follow the input. Okay, so this is how your interiors of the tri-state buffer looks like. Let's look into the characterization setup for now. So this is the tri-state buffer. So we have taken the subcircuit of the tri-state buffer and created a symbol for the tri-state buffer. So you have this input pin for which we apply the pulse waveform. You have the enable pin for which we are applying the pulse waveform. You measure the output over here, and this is the supply connection. So what you have from here, if you see this, if this was your input waveform, which you, so these are all spice simulated waveforms. We'll get back to the spice simulations and the characterization in the part 2 course. So let's look into the waveforms first. So if you have this input as, if you have these waveforms as their input, you have these waveforms as the enable pin. So if, what we have done is we have made the enable pin high and low at different periodic intervals. So whenever your enable is low, your output goes into the high impedance state. I'll show that in a moment from now. And whenever your enable is 1, it should follow the input. That's the idea. So, and that's what we see at the output. Whenever your enable is 1, you see the output follows the input, and whenever your enable is 0, output goes into the high impedance state. So now let's try to focus into this high impedance state, or let's try to focus into the output whenever the enable goes into the 0 or goes into the logic 1. So we have the waveforms collected over here. So if you try to closely look in this particular waveform, this is the red one is your enable signal, okay, and the blue ones is your output signal. I have not shown the input because input is the same one which it follows whenever our enable is equal to 1. Now looking into the state table that we had drawn, so we need to find out the different transitions. So first, let's say we will identify the high impedance to the logic 0. It says that your output was in high impedance state. Now it enters into the logic 0 state, and this is what it is. So it was in high impedance state whenever your enable pin was 0. The output was in high impedance state, and whenever your enable turns equal to 1, it moves from the high impedance state to the logic 0 state, and there is a transition value present over here, and this slew value needs to be computed for. Okay, next we have the high impedance state to the logic 1 state, and these are the two different points. So whenever your enable pin is 0, your output is in high impedance state, the blue one, and whenever your enable moves to logic 1, it moves from the high impedance state to a logic 1 state, and this is another slew that needs to be computed for. Okay, next is logic 0 to high impedance state. So whenever your output is logic 0, and when your enable pin is given as a 0, it moves into the high impedance state. So this is the transition points. Whenever your enable was initially 1, but then when it moved to 0, your output has to move to high impedance state, and there is a transition that happens from logic 0 to the high impedance state. So there is another slew that needs to be computed for. And finally you have the logic 1 to high impedance state. So whenever your enable initially was 0, and then it became, whenever enable was initially 1 and then it became to 0. So this is the state where your enable was initially 1 and then it came back to 0. So your output moves from logic 1 to the high impedance state. So now there are different characterization setups for measuring the 4 different slew values. So we'll get back to that when we enter into the part 2 of the Guna tool. So for now, let us try to understand. So these are the 4 different characterization points that we need to identify, or that we need to compute for when we go into the characterization tool. So what we'll do is we'll stop at this point, and from the next video we'll look into the next timing characterization parameter, which is setup, hold, recovery and removal for a day flip-flop. So let's try to begin with the next timing characterization setup from the next video. Thank you.